This video is part of a self-study course on refrigeration and heating operation, diagnosis, and service. It is the first of two self-study courses, a multimedia course, and an instructor-led course in the climate control training curriculum. It should be used with the Refrigeration and Heating Operation, Diagnosis, and Service Training Reference Book. To achieve maximum learning from this self-study course, read the appropriate pages of the Refrigeration and Heating Operation, Diagnosis, and Service Training Reference Book before viewing the corresponding portion of the video. Ford customers depend on their vehicles. They rely on them in all types of climates, regardless of the weather, from the coldest northern winters to the searing heat of deserts. Ford customers expect their vehicles to transport them in comfort. Ford climate control systems provide our customers the comfort they expect, no matter what the conditions are outside the vehicle. As a Ford climate control service technician, you are the person who must understand a vehicle's climate control system. And when the system isn't working correctly, you're the person that has to accurately diagnose and repair it. To best perform these tasks, knowledge of the basic principles of refrigeration and heating is essential. Before continuing this video, stop the tape and read these pages in the Refrigeration and Heating Operation, Diagnosis, and Service Training Reference Book. Humans are the most versatile creatures to ever walk the surface of the earth. We have spread to every corner of the globe and have adapted to conditions that would have destroyed other species. However, for all our adaptability, we are really very fragile. We attempt to live our lives in a very narrow temperature range. This range is generally between 60 and 80 degrees. Usually when the temperature is below 60 degrees, we look for ways to increase the temperature. Conversely, when the temperature is above 80 degrees, we look for ways to reduce the temperature. Only within the past century have truly effective methods of mechanical heating and cooling been developed. Although there are many different types of heating and cooling systems, they all have one common purpose: to introduce or remove heat. They accomplish this using the 6 principles of heat transfer. These principles include: heat travels from hot to cold, the latent heat of vaporization, the latent heat of condensation, changes of state do not change mass, boiling and condensing points change with pressure, temperature changes with pressure. Let's look at how these principles are used in heating and cooling. Heat is a form of energy. It has a relationship to the atom. The atom is the smallest part of an element. Groups of atoms combine to make molecules. Atoms in a molecule are in a constant state of motion. Adding heat to the atoms increases the rate at which they move. Removing heat will slow the atoms down. This is why adding or subtracting heat from a substance will cause the substance to change physical states. Substances can exist in 3 physical states: solid, liquid, or gas, depending on their temperature, pressure, and heat content. Look at the different states of water. At sea level atmospheric pressure, between the temperatures of 32 degrees and 212 degrees Fahrenheit, the movement of the water's atoms allow it to maintain a liquid state. However, if heat is removed and the water temperature falls below 32 degrees, the motion of the water's atoms will slow enough for the water to change physical states and become ice. Raising the temperature of the water above 212 degrees will also cause a change of physical state. If this occurs, the atoms will speed up enough for the water to become steam. The first principle of heat transfer is that heat always travels from hot to cold. This is because the faster moving atoms give off some of their energy to the slower moving atoms. In each of these examples, you may have noticed that temperature affects the speed of motion of the atoms. In fact, temperature is a measurement of the motion of atoms. It is important not to confuse heat, which is a form of energy, and temperature, which is a measurement of atomic motion. The reason it is important is because there are different types of heat. The first type of heat is called sensible heat. Sensible heat causes only a change of a substance's temperature. Sensible heat is the type of heat that is measured with a thermometer. Latent heat, which is also called hidden heat, is the heat that causes a substance to change physical states without changing temperature. For example, water can reach a temperature of 212 degrees Fahrenheit and still remain liquid. However, once the water absorbs enough latent heat, it will change physical states and become steam. This occurs even though the steam's temperature is still 212 degrees. This principle also works the opposite way when water changes from gas to liquid. Enough latent heat must be lost before 212 degree steam converts to 212 degree water. Once the latent heat is lost, it will change to water that has a temperature of 212 degrees. This principle is the latent heat of condensation. Mechanical refrigeration equipment uses the refrigerant's ability to absorb and release latent heat when changing physical states. The heat content of a substance is measured using the British thermal unit, commonly called the BTU. 1 BTU is equal to the amount of heat required to raise the temperature of 1 pound of liquid water 1 degree Fahrenheit. However, it should be noted that to increase the temperature of either ice or steam 1 degree, the addition of only 1/2 of a BTU is required. Now, let's put all this information together. The ice in this container weighs 1 pound and is at a temperature of -40 degrees. To raise the temperature of the ice 72 degrees requires the addition of 1/2 BTU per degree, a total of 36 BTUs. Adding this heat increased the ice's temperature to +32 degrees, but did not cause it to change its physical state. This is an example of sensible heat. In order to change the ice into water, we must add another 144 BTUs of heat. The addition of this heat will cause the ice to melt, but the temperature of the water it changes into is still 32 degrees. Since this heat caused the substance to change physical states, but not temperature, the additional heat is hidden. This is an example of latent heat. Moving along, we can see that it requires another 180 BTUs to increase the water temperature from 32 to 212 degrees, 1 BTU per degree. This again is sensible heat. However, to get the 212 degree water to convert into 212 degree steam requires that it absorb another 970 BTUs of latent heat. As you can see from these examples, a great deal more latent heat is required to change a substance's physical state than the sensible heat needed to change the substance's temperature. As with all substances, the weight of the water does not change when it changes state. 1 pound of water weighs the same, whether it's solid, liquid, or vapor. Another important principle is that the temperature at which a substance changes states will vary depending on its pressure. At an altitude of almost a mile, water in Denver, Colorado boils at less than 212 degrees. Lower atmospheric pressure at Denver's high altitude lowers the boiling point of water. Because of the high pressure in a vehicle's radiator, water can be much hotter than 212 degrees and not boil. However, if the radiator cap is removed, releasing the cooling system's pressure, the water will instantly begin to boil out. Up to this point in the video, we have used water to demonstrate the principles of heat transfer. Let's now look at how these principles affect refrigerant during the operation of an automotive climate control system. Refrigerant enters the air conditioning compressor as a vapor. This vapor is at or slightly below ambient temperature. As the vapor is compressed, the mechanical energy of the piston's movement is transferred to the vapor, and its temperature rises. The increased pressure caused by compression also increases the temperature at which the refrigerant will condense and change from a vapor to a liquid. As the hot, high-pressure vapor leaves the compressor, it enters the condenser. The cooling action of the condenser quickly reduces its temperature below its condensation point. During condensation, the change of physical state releases the latent heat stored in the refrigerant into the air passing over the condenser. You have now learned the 6 principles of heat transfer. Let's quickly review them. Heat travels from hot to cold. The latent heat of vaporization. The latent heat of condensation. Changes of state do not change mass. Boiling and condensing points change with pressure. Temperature changes with pressure. Before continuing this video, stop the tape and read these pages in the Refrigeration and Heating Operation, Diagnosis, and Service Training Reference Book. Automotive climate control systems must be very powerful and compact. This is necessary because of vehicle space limitations and the wide range of climates in which cars and trucks operate. During the summer, solar energy and the heat generated during vehicle operation will put the air conditioning system to the test. While in the winter, the heating system must maintain comfortable driving conditions regardless of wind and temperature. Let's begin this part of the video by looking at the air conditioning system. Ford Motor Company uses two different types, the fixed orifice system and the thermostatic expansion valve system. Let's first look at the components and operation of a fixed orifice system. Beginning at the outlet or high pressure side of the compressor, you can see that during the compression stroke, the volume of refrigerant vapor is reduced. As this occurs, the temperature and pressure of the vapor increases. This higher pressure raises the refrigerant's condensation point. The vapor then enters the condenser, where latent heat transfers to the cooler ambient air, which is moving across the condenser coils and fins. This causes the refrigerant to change states and become liquid. The liquid refrigerant then moves to the fixed orifice. The orifice creates a restriction in the system. This restricts the amount of refrigerant that can pass through the orifice, creating lower pressure at the outlet of the orifice than at the inlet. This causes the pressure to be lower in the evaporator and suction accumulator dryer than in the condenser. The low-pressure liquid refrigerant then enters the evaporator. Because of the lower pressure, the refrigerant's boiling point is reduced to about 32 degrees. The fan in the passenger compartment blows warm air over the evaporator, causing latent heat transfer to the liquid. This causes the refrigerant to boil and change states from liquid to vapor. This low-pressure vapor is drawn from the evaporator and into the suction accumulator dryer. There, any moisture in the vapor is absorbed by a desiccant bag. The refrigerant, along with a small amount of oil, is then drawn into the compressor during the intake stroke. This completes one refrigeration cycle of a fixed orifice system. The second system that can be found on Ford vehicles is the thermostatic expansion valve system. An air conditioning system using a thermostatic expansion valve also has a receiver dryer instead of a suction accumulator dryer. The thermostatic expansion valve uses pressure differential to control refrigerant flow through the system. The valve accomplishes this using a ball and plate assembly and expansion valve spring, which is opposed by a diaphragm connected to a capillary tube with a sensing bulb. During operation, refrigerant comes into the valve from the condenser. The expansion valve spring presses against the ball and plate, trying to close the valve and prevent refrigerant flow. Opposing the expansion valve spring is the diaphragm. Pressure generated by the sensing bulb moves through the capillary tube and builds up behind the diaphragm. If the pressure is high enough, the diaphragm forces the ball and plate away from its seat and refrigerant is allowed to pass to the evaporator. The pressure that moves the diaphragm is generated in the sensing bulb. Filled with temperature-sensitive gas, the sensing bulb connects to the outlet line of the evaporator. If the vapor leaving the evaporator is hot, the gas in the sensing bulb expands, generating more pressure against the diaphragm. This forces the ball and plate away from its seat, allowing more refrigerant to flow to the evaporator for better cooling. However, if the vapor leaving the evaporator is cool, the expansion valve spring will overcome diaphragm pressure and move the ball and plate towards its seat. This action restricts refrigerant flow when cooling requirements are low. Located between the condenser and thermostatic expansion valve, the receiver dryer acts as a refrigerant reservoir. When cooling demands increase, refrigerant stored in the receiver dryer is sent to the thermostatic expansion valve as required. The receiver dryer contains screen-type filters and a desiccant bag to remove moisture. All air conditioning systems have control switches and safety valves incorporated into their design. These switches and valves include the AC cycling pressure switch, which controls compressor clutch operation on fixed orifice systems to prevent evaporator icing. The thermostatic de-icing switch controls compressor clutch operation to prevent evaporator icing on thermostatic expansion valve systems. The high-side pressure relief valve protects AC components from damage in the event excessive pressure builds up inside the AC system during operation. The low-side pressure relief valve found on some vehicles equipped with R134A systems prevents component damage which may occur due to pressure buildup caused by high ambient temperatures. The final switch we'll cover is the AC high-pressure cutoff switch. This switch comes in two types, a single-function version and a dual-function version. The single-function cutoff switch has only one function, to interrupt compressor operation in the event of excessive high-side pressure. The dual-function cutoff switch performs two functions. First, it will control the condenser cooling fan to attempt to lower high-side pressure. However, if the pressure continues to rise, it will also interrupt compressor operation. These steps are taken to maintain refrigerant pressure below the release setting of the high-pressure relief valve in order to prevent the release of refrigerant into the atmosphere. We now come to one of the most important components of the air conditioning system, the refrigerant. While there are many types of refrigerants used in non-automotive applications, until recently only R12 was used in automotive systems. The drawback to R12 is that it contains chlorofluorocarbons, usually called CFCs. CFCs contain chlorine. Some scientists believe that when R12 is released into the atmosphere, its chlorine atoms destroy the molecules that make up the ozone layer. The ozone layer is a part of the upper atmosphere above the Earth. It helps reflect the sun's ultraviolet radiation away from the Earth. Scientists believe that depletion of the ozone layer by CFCs allows an increased amount of harmful ultraviolet radiation to reach the Earth's surface. For this reason, legislation controlling R12 was adopted. This legislation controls the production and handling of R12 and also mandates that all automotive air conditioning systems be manufactured with non-CFC refrigerants as of 1995. Ford Motor Company began producing its AC systems with non-CFC R134A in 1992. As of the 1994 model year, Ford cars and light trucks use R134A refrigerant. There are some exceptions to this, so always check the vehicle refrigerant charge tag. Ford Motor Company clearly states the type of refrigerant found in the AC system on the refrigerant charge tag. However, during air conditioning system service, always use a Rotunda refrigerant identifier tool to verify the type of refrigerant in the system. If the system contains the wrong refrigerant, it must be evacuated and the contaminated refrigerant disposed of properly. Then use the Rotunda air conditioning flusher to clean and flush the AC components. R12 and R134A air conditioning systems have some important differences. Never interchange components of an R12 and R134A system unless specifically directed to do so by a Ford service publication. Another important difference is that R134A systems have larger quick disconnect service charge ports to prevent accidental connection of an R12 service station to an R134A system. Different lubricating oil is used in R134A systems. Use only YN12 PAG oil when servicing an R134A system. An R12 system uses YN9 mineral-based oil. Whenever servicing any air conditioning system, always refer to the service manual for correct service procedures. Before continuing this video, stop the tape and read these pages in the Refrigeration and Heating Operation, Diagnosis, and Service Training Reference Book. An automotive heating system works opposite of the air conditioning system. The heating system draws heat from the engine coolant and transfers it into the passenger compartment. This is achieved by routing hot engine coolant from the engine block into a small heat exchanger called a heater core. The blower motor and fan, which is the same one used for the air conditioning system, circulates air through the heater core. This transfers heat to the cooler passenger compartment air, which increases the passenger compartment temperature. To improve the efficiency of the AC system, some vehicles use a water valve to prevent the flow of hot coolant into the heater core during AC operation. The water valve is usually mounted in the inlet hose to the heater core, but on some vehicles it may be mounted in the inlet of the heater core itself. Although the heating system is very simple in design, be aware that any defective component in the engine cooling system may affect its operation. This includes the water pump, radiator, radiator hoses, thermostat, engine water jackets, head gaskets, coolant recovery reservoir, engine cooling fan, heater core, and heater hoses. Before continuing this video, stop the tape and read these pages in the Refrigeration and Heating Operation Diagnosis and Service Training Reference Book. Diagnosis of a vehicle's climate control system requires that a logical diagnostic procedure be followed. An effective technique of logical diagnosis is the symptom to subsystem to component to cause method. This method of diagnosis will enable you to go from the symptom of the concern to the cause using a logical diagnostic process. Let's look at how to use the symptom to subsystem to component to cause diagnostic method. The first step when diagnosing a concern is verification. Ensure that you understand the customer's description of the concern. Then try to get the concern to occur while you are operating the vehicle. Next, you must identify the vehicle operating conditions when the concern occurs. Vehicle operating conditions include items such as vehicle operating temperature, driving conditions, and/or any other condition that exists when the concern occurs. Clues to the concern may also be found by noting under what conditions the concern disappears. Correctly interpreting the customer concern will enable you to determine the vehicle's symptom. Once the symptom and the conditions are known, consider which climate control subsystem is causing the fault to occur. There are 4 basic subsystems of the climate control system. These are the refrigeration system, which includes the compressor, condenser, fixed orifice tube or the expansion valve, evaporator, suction accumulator dryer or receiver dryer. The heating and engine cooling system, which includes the heater core, heater hoses, water valves, and the engine cooling system. The control system, which includes the control head, input sensors and output actuators, blower motor and circuit, and the compressor clutch circuit. And lastly, the air management system, which includes the plenum, air inlet door, temperature blend door, and the air distribution doors. If the vehicle has a manually controlled system, look in the service manual to determine the correct pre-checks. Pre-checks are preliminary tests that are relatively simple yet very important. Sometimes the cause of the concern will quickly be found using pre-checks, but not always. Even when the pre-checks don't reveal the cause of the concern, they always eliminate possible causes. If the pre-checks don't reveal the cause of the concern, turn to the symptom chart in the service manual. This chart uses the symptom to subsystem to component to cause method to help you to quickly find a problem. When using the symptom chart, first look at the condition column and follow it down to the symptom of the vehicle. Then move to the possible source column. This is a list of items that might cause the symptom. From the possible source column, go to the action column. This column will direct you to perform a specific test procedure. Always perform these tests exactly as described. Never skip steps or perform them in the wrong order. When interpreting the test results, always compare your findings with the specifications in the service manual. Once you've found the faulty component, try to determine the cause of its failure in order to prevent a reoccurrence. For example, the symptom of poor cooling may be the result of low refrigerant in the system. But what caused the refrigerant to be low? The cause must be determined and corrected. If not, the symptom will reoccur. Once you have performed the required repair, the final step is to verify that the concern is corrected. When doing this, operate the vehicle in the conditions that the concern occurred. This helps ensure that the vehicle is fixed right the first time. We hope you found this video and training reference book helpful and informative. This is the first course in a complete training curriculum on climate control systems. Be sure to complete the remaining courses in this curriculum. These include Air Management and Controls, Operation, Diagnosis, and Service Self-Study Course, Climate Control Systems Diagnosis Ford Multimedia Training Course, and Advanced Climate Control Systems Diagnosis Instructor-Led Training Course.